what is the basics of threshold voltage. Now we will see how the energy band diagram of an inversion region is taking place. See, there is this energy band diagram has got a valence band, okay, and a conduction band. Between the valence band and conduction band, we have this energy band diagram. And what is the minimum energy that is required is 2 times phi f. Okay, this is the Fermi level energy which is required to make your MOS to get into the conductivity band. Okay, so this 2 times phi, this is phi f and this is minus phi f value. Okay, this is between the valenced and the semiconductor part. Okay, this is the intrinsic band region. This is the valenced band. This is the Fermi. In between the valenced and the intrinsic band, you see this EF. This is the Fermi level. Okay. Now this in between these two levels, there is an energy band of phi f and minus phi f. Put together, this is the total sum of 2 phi f. Generally, it is a difference. The value is evaluated by the difference of both. So phi f minus phi f will give you 2 times phi f. This is the minimum energy that is required for the MOS to go to the inversion layer, or in other words, a channel is created only when this particular energy band is obtained. Means that the conductivity starts. Okay, so I think this we have already dealt in the last class. I'm just iterating it back. Now, what are the parameters? What are the parameters that are required for the threshold voltage, right? To sum up what we have learned what is threshold voltage and what is the band of energy required and how is the threshold voltage created and what it happens after creating a threshold voltage, an inversion channel is being created, right? So what the definition of this thing is, threshold voltage is the minimum voltage that is required for the inversion layer between source and drain. Okay, if it is less than the threshold voltage, then the device is in off state. That's why this voltage is very important, and we are going to see what are the parameters. Okay, when you take the parameters of threshold voltage, please remember there are 4 parameters. How many parameters are there? There are 4 physical parameters which are going to affect the functioning of MOSFET. Okay, now we'll see in detail and we'll also derive each parameter and see how the threshold voltage is derived, right? The first and the foremost parameter is the work function difference between the gate and channel. Okay, this is a differential value of work function which is given by phi of f. Okay, this is between the metal and the channel region. Between the metal and the channel region, there is a workforce energy which is required. This is the first parameter. Okay, these are physical parameters which affect the threshold voltage. The first physical parameter is work function difference between the metal and the channel. Gate is nothing but the metal region and the channel region. And the second we'll study in detail as we go down. So just keep this in your mind. The first parameter is it's a difference between the metal and the channel region. The second region is the gate voltage component. Okay, that changes the surface potential. So when the surface potential is changed, what would be the gate voltage? How would be the gate voltage component? We will derive it. Okay, so you'll learn it in detail. When what happens when the gate voltage, that is a positive voltage, is applied, this positive voltage goes down into the depletion region. It forms an ion, and what is the impact of that ion on that particular region? So that creates a voltage, because ions, when they move, they create charge flow and automatically a voltage is created. So that voltage component has to be taken into consideration. That is the second parameter. Third one is the gate voltage component offset. Okay, this is offset voltage that is created and that creates a charge. Okay, so this charge is given to be QB, that is created because of the charge movement in the depletion region. Okay, and there are 2 types of effects because of it. If the I told you there is something called bulk voltage, right? There is a bulk component. So you will study if without bulk, if you don't have bulk voltage, how would be this charge in the substrate in the depletion region created? And if the bulk voltage is considered, how would be the effect? So both the things you will be studying in detail. So that is the third component, that is gate voltage component offset in the depletion region. And the last one is the fabrication geometric change. Okay, this is because of the fabrication, there might be an offset in the fixed charges. Okay, so how would be those effects? Okay, so because of the fabrication, there will be a change in the dimetrics of the system. Okay, that is the fourth parameter. Okay, so first parameter, there are four parameters. Please remember, there are four parameters that affects the threshold voltage. The first one is the work function between the metal and the channel. The second one is the charge. Okay, that is caused due to surface potential. Third one is the offset in the depletion region, and the last one is the fabrication dimetrics, which causes the change in the fixed charges in the gate oxide. Okay, so we'll see in detail how these four parameters are used to construct the threshold voltage, right? So we will see each parameter by parameter in detail, and we'll derive this threshold voltage. Okay, so as of now, we have seen two topics. We have completed what is basics of threshold voltage. Second one, we have seen what are the parameters. How many parameters are there which governs the threshold voltage? Can I have Mr. Jabba Suvin? His name is right. Jabba Subin,
Yes,
are you there? So, Jabba Subin, how many parameters are there, ma, for threshold voltage? How many parameters are there in the threshold voltage of a MOSFET? Just tell me how many parameters, na? Nitish Kumar. Jabba, you are doing always the same thing. This is the second class, you are iterating the same response. Jabba Subin. Okay. Nitish Kumar. Nitish Kumar. Nitish Kumar. Yes, sir. How many parameters are there for your threshold voltage of a MOSFET? How many parameters are there? Give it in the chat, man, if your mic is not working. Fast. Yes, Nitish, that's right. Thank you. So there are four parameters. We'll see in detail about all the four parameters now. Right. The first parameter, as I already told you, it is the difference between the metal and the channel. Okay, it's the work function, which is a difference between a metal and the channel. Metal, why I tell metal is it's almost the gate, polysilicon region. Okay, so that is the top region. I told you in the construction, this particular part, metal oxide semiconductor, this particular part and the substrate. So that work force, which causes this bend. Okay. So this property is given by a difference of the substrate as well as the metal. Okay, the substrate is given to be Fermi level phi f minus your metal region, it is phi m. Okay, that is the first work function difference. That's the first parameter we studied. The first parameter is the work function difference between phi of gs and the channel, between the gate and the channel, in other words, right? Now talking about that's the first parameter. That's how you estimate the first parameter. Phi of GC is given to be phi of F minus, that is the substrate part, minus phi of M, which is the metal part. Now going to the second part, second parameter, that is the surface inversion. Okay. Now surface inversion is nothing but you apply a surface potential. Okay. When you apply a surface potential, there is a shift in the Fermi level. Okay, the shift is given to be a difference of both the values. So what would be the total difference? This is phi f minus of minus phi f. So the total Fermi shift or the surface inversion value is given to be 2 times phi f. Okay, that's what you'll be deriving. So it is the difference between from phi f to minus phi f. So from the energy band diagram, it is given to be a difference of the value. And when you evaluate it, the total value is given to be minus of 2 times phi f. Okay, this is the second parameter. So we have studied two parameters. The first one is work function difference between gate and channel. The second parameter is the surface inversion. Surface inversion is given to be 2 minus 2 times phi f. Right? Now the third parameter. The third parameter is nothing but the voltage that is applied at the gate terminal. When you apply an voltage at the gate terminal, what happens? The charges starts building, right? You're applying a voltage that's going to be a positive charge, which is nothing but hole. The hole is going to come inside the gate region. Okay. And because, look at this, this is the gate, you apply a positive voltage. So a positive voltage is going to come here. This positive voltage will come and it will enter into this gate. Okay. Via this gate, it enters into the depletion region. So once this hole enters into this particular region, it becomes an ion. Okay. Once it gets transported, it becomes an ion. So once it becomes an ion, what happens is it starts moving, right? Generally, holes, when the ion starts moving, there is a charge created. Because of the charge, a voltage is created. Movement of charge creates, what happens when the movement of charge creates? There's a flow of electrons or holes that creates a voltage, okay? And that voltage is causing this effect in the depletion region. Okay, and this voltage in the surface inversion part is given to be a value of Q of Bs. Charge is given to be Q of B naught. Okay, this is the surface inversion charge density. Okay, and it is given to be a factor of 2 times Q. Na is the acceptor ion. Si is the permittivity of silicon. And 2 times phi, you already know what is 2 times phi. This is the surface inversion potential, right? So these parameters will be the charge density that is created in the surface inversion region, right? Now this is without the bulk voltage, which is, I don't apply the bulk voltage. I don't consider this bulk. Okay, if I don't consider this bulk, the expression is what we have studied now. Okay, when you consider the bulk means you're applying a voltage across substrate and bulk. Okay, so when you apply that, it becomes, there is another extra voltage added to the expression, that is plus VBS. Okay, practically it is like this. Theoretically, they will tell they will not consider this, but when you're going to a practical MOSFET, it will be QB into minus 2QNA epsilon I into 2 times phi s plus one more constant will be involved, that is called VBS. Okay, now this is the third parameter. Okay, in third parameter, please remember there are two aspects in it. One is without the substrate and with the substrate biasing. Okay, here there is no substrate taken into consideration. We just study the charge with respect to the surface depletion. And when you have the substrate, the equation changes to this format. Okay, now we have studied all three parameters. One is work function difference, that's called phi of GS. Second parameter is surface inversion. Surface inversion is given to be 2 times phi f. And the last one is the surface inversion charge density, that is QB. That is nothing but 2 times Q into Na into epsilon I into 2 times phi f. Please go through your textbook. You have the derivation for this completely, because if I take that, it will go for a long time. So the derivation is there in the textbook. If you want to refer how this formula is derived, you can very well do with the textbooks. It's there in your Google Classroom, right? So when you take the surface diffraction inversion region, there are two parts. One is without the surface substrate biasing and with substrate biasing. So these are the two equations. So as of now, we have done with 3 parameters. Now we'll go to the last parameter for the day. That is the fourth parameter. Okay, the fourth parameter is with respect to the I told you in the fabrication there is a lattice imperfection taking place. Okay, because of the lattice imperfection taking place, there is a change in the threshold voltage. Okay, lattice imperfection means the shape. When you fabricate the whole IC, there will be a small imperfection. That's called lattice imperfection. And that will also affect the threshold voltage. So that has to be taken into consideration. That is given to be because of the fixed charge QOX by COX. This is the thickness of the oxide. Here OX is nothing but the oxide. So QOX by COX is the value of the fourth component that is crossed because of the lattice imperfection in the fabrication process. Okay, that is when they're making the IC. So that is the fourth parameter. Okay, now to sum up, we have studied all the four parameters: work function, surface inversion charge density, and the last one is lattice imperfection, right? Now, how do you calculate the threshold voltage? Now, all these four parameters, you just add it. Okay, the sum of all the parameters, please keep in mind, you are not considering the substrate biasing. Substrate biasing is the bulk voltage. You're not taking any substrate biasing into consideration. Without taking substrate biasing into consideration, you just add the first one. What is first one, ma? Phi of GC. Okay, you add phi of GC. Second one, that is the gate channel substrate. The second one is you have the inversion region, surface inversion. So surface inversion is given to be 2 times phi F. And then you are considering the third one, that is a charge. And the last one is the fourth component, which is the lattice imperfection. Just add all the three things. Okay, this is the first condition. You are estimating what is the VTO, that is the threshold voltage. Now, when you have zero biasing, this is the voltage. When the zero biasing is taken over, you apply a voltage, automatically this particular term, look at this particular term, Q of VO. This is when it is zero biasing. If you are increasing the biasing, the value of QB will vary. Okay. Now you have to estimate how will this variation affect the threshold voltage. Okay. There are two types of inferences you have to do. One is zero substrate biasing, non-zero substrate biasing. In non-zero substrate biasing, when the voltage is increased, the equation changes to this particular value. Okay. Now I am taking the common factor COX and I introduce another concept. Okay. This is nothing but the expression modifies to this format. Okay. That is BOX minus QOX by COX minus BOX minus BOX by COX. This is the effect because of the non-zero substrate biasing. Okay, non-zero substrate biasing makes the threshold voltage to this fluctuation. Now, when you, so what I'm doing is to, in order to make this equation simplified, this whole thing, what is this till here? What is the whole thing? This whole thing is made into VOT. Okay, this is at zero biasing, it is VOT. So I'm just substituting this value over here. Okay, so what is the remaining leftover? Till here it is over, right? Till here it is VOT. So VOT minus this factor alone. So your threshold voltage is equal to VOT minus QB minus QB0 by COX, where COX is nothing but the capacitance across the oxide region. Okay, is that clear so far? So there are four parameters. We have studied the four parameters and we have estimated what is the threshold voltage. Okay, now for the to make the whole thing little more simpler, I take this particular value. I'm just taking the second part, this whole value, that is QB minus, what is QB minus QBOX? Okay, I'm just going to make it in terms of voltage because everything is terms of voltage. This is in terms of charge. So I'm going to make it in terms of voltage. So what would be the value is, you already studied what is QBX. What is QBX by COX? We already know what is QBO. What is QBO? The third parameter. We have learned the third parameter. What is QB? QB is nothing but 2 times Q into Na into epsilon Si into 2 times phi f. So that we already studied. The same thing I'm just taking both. Okay. I'm taking QB and QBOX. So I'm just substituting it. I'm taking the common terms. Which is common to both? you have this particular term, which is common to both. Okay, which is common to both QB and QBOX. So I segregate that particular term outside and write the remaining over here. Okay, so this is the expression for this. Now, how would, if I simplify it, the whole expression is going to be VTO. Okay, this whole thing, this VTO, I'm just writing as a VTO. So this is in terms of charge. So I want to convert it into voltage. So this is what the reason why I do this. And after that, I simplify it, I get a constant called gamma. Okay, this gamma is because of the substrate biasing. That is called as body effect coefficient or substrate biasing. Okay, this full thing comes into gamma. This whole thing changes to gamma. Okay, it changes to gamma, which is nothing but the substrate biasing. So that is given to be root of 2q Na into epsilon I by COX. Okay, that is the expression for gamma into this particular value. Okay, so this is what the threshold voltage is all about. The derivation clear? It depends on the 4 parameters. Just write the 4 parameters. The rest is all substitution. Just add all the parameters, you will get it, right? To sum up what we have learned for the day, we've seen what is the basic of threshold voltage. We saw what are the parameters. There are 4 parameters, and how do you derive the 4 parameters and estimate the threshold voltage, right? So that's what we have learned for the class. So to sum up, threshold voltage is the minimum voltage that is required for the formation of the inversion region or the channel between the source and the drain. Okay, so if the threshold voltage, if the voltage is less than threshold voltage, then your VGS value or the MOS would be in the cutoff region, right? So this is the energy band diagram. We saw what are the 4 parameters. The first one is work function between gate and metal and the channel region, and then the surface potential, then the voltage component, and then the last one is the fabrication process glitch. Okay, that is the 4 parameters. We saw individually how to get the work function between the metal and the substrate, and then we saw how to get the inversion, surface inversion, and then how to get the charge density of the surface inversion. When the substrate voltage is 0, when you apply the substrate voltage, how would be the voltage? And then the last parameter, it is because of lattice imperfection, which is in the fabrication process. So how do you estimate is the total of everything, all the 4 parameters, you get the threshold voltage. And then when you, this is for the first condition. Condition 1, it is substrate biasing is 0. When there is substrate biasing is changed, the equation changes to this format. So you simplify it and write it in this format. And then you make it in terms of voltage. The voltage is given to be Vt is equal to Vt naught plus gamma into root of 2 phi f plus Vb minus root of 2 phi f. Okay, where gamma is the substrate bias of the body effect. Is that clear? So just go through this whole thing. I will share it in your Google Classroom for your kind reference. Please